Morning, everyone. This is Boyan. So today our first keynote speaker is Professor Michael Dickey. Uh, Professor Dickey graduated from University of Texas, I think it's in 2006. And then he went to do a postdoc at Harvard at George Whiteside's group, and then for 2 years. And then he started his career for 16 years in NC State University. So today, I believe he will give us a really nice talk about using the soft matters with the liquid metal and how do they integrate together to make a software buds. So just a small fun fact between how I know Professor Dickey's research. That is like at my first year of my assistant professors back to Singapore, I was like thinking about what kind of research I'm doing. So I'm like brainstorming within myself, and then I I have the ideas. Oh, I want to fit the liquid metal into the soft matter to make a soft robots. But after I started to look at the Google Scholar and then look at the literatures, I found out that his work is all over the place in this area. So now make me decided, oh, I'm not going to this direction, although it's very interesting, but I would like to do the other directions. Uh, just want to say that he has done a lot of work, over like 200 literatures publication in this field. So it is my pleasure to introduce Professor Michael Dickey to you, and I'm very glad we can hear his talk today. Thank you.
I like to walk around. I'm wondering if I can speak loudly like this. Can everybody hear me? Yes. Okay. So, well, first of all, thank you for the introduction. Thank you all for having me. I'm really happy to be here and share with you some of the work that we're doing in NC State. We don't work on robotics directly, but a lot of the materials and stuff that we do work on has applications for robotics. And so I'll try to make that the theme of my talk. Before I tell you about the kind of the title of work here, liquid metals, I thought I'd just tell you a little bit of an overview of some of the stuff that we do. So our group is united by the importance of these words: interfaces, patterning, and soft matter. And well, these are kind of vague words that are meant to encompass a lot of different things. So let me give you a couple examples. So over on the left here is some work we've done on self-folding. This is a plastic sheet. You have to watch because this happens really quickly. So this is a plastic sheet that we patterned in 2D. We then shine light on it and get it to fold. So the idea here is that there's many ways to make two-dimensional patterns. This is how computer chips are made, inkjet printing, all these kinds of things work in 2 dimensions. This is a way of taking that and making it in 3D. And then more recently, we've taken this idea and worked with Nathan Lazarus, who's the other keynote speaker today. And the idea was to take printed circuit board materials, which are also made in two-dimensional planar processing, and use a single tool, which is a laser, to both cut the material at high powers and then at lower powers get the material to fold. So again, the idea here is to take a two-dimensional process and make a three-dimensional object. You might notice there's an LED in the middle, and it continues to work the whole time, which just shows that the function of this device is not compromised by this folding process. Okay, so there's that. We also work on polymers. And so we're in particular working on gels. And so those of you that wear contact lenses have experienced hydrogels. This is all Jello, tofu, these are all hydrogels. They tend to be very soft and not very good, have very good mechanical properties. So here we've made something that looks like a drum, like a bongo drum. And again, watch, because this happens very quickly. We drop a metal ball and it just tears, as you would expect. But more recently, we've figured out a way to make these materials tougher. And so here we drop a ball and just get it bounce right off this gel, even though it contains 60% liquid. So that's a little tease of things I'm not going to talk about. So sorry about that. But I'll be happy to talk with you during the breaks. I am going to talk to you about this work on liquid metals. And the motivation within the context of this community is to make things soft. Why would you want to do that? Well, existing devices like your cell phone or your computer or a robot tend to be made out of rigid materials, which is in stark contrast to the human body, which of course is made mostly out of soft materials, but yet can do amazing things. So there was some work done maybe 15, 20 years ago at Harvard that introduced this idea of soft robots, and actually builds on work that goes even further back from Japan. But anyway, this is some work that's from Whiteside's group. And it's basically like a balloon. It's a piece of rubber that's got these cavities inside of it, and and in this example, it's being inflated with some pressure. That causes it to expand a bit. Now, why would you want to do this? Well, for one thing, it's like an octopus has a high degree of freedom, motion, right? It can squeeze inside of a bottle and then come out. So there's that, and then also it can interact safely with the human body. So there's a number of advantages of making things soft. There's some disadvantages as well. But we've been trying to figure out, well, how can we add function to these kinds of materials? So we want to use soft materials, of course. And this is a plot of modulus of different materials. So way over here is diamond. That's, of course, very hard. If you go a million times softer, you'll find rubber, which is what was in that previous video. Go 1,000 times softer than that, you'll find biology, muscle, brain tissue, etc. Go way over here, you'll see liquid metals. But that's interesting because metals can have electricity. They add function to the types of devices that I showed you. So the material that we're using is basically gallium. This is a picture of gallium. This is in its solid state. It's a crystal here. And if you held this in your hand, your body is warm enough to melt this. This is about 86 Fahrenheit. However, we don't want to use our body temperature to have to melt it, so we add in another metal, indium. And when you mix these two things together, you get a liquid. Really a liquid at room temperature. Got a lot of interesting properties. It does not evaporate, so you don't have to worry about breathing it or having it go places you don't want it to go. It's got a viscosity like water. It's got low toxicity, so a lot of appealing things. But for us, the most important thing is that it reacts with air. It forms a very thin oxide on its surface. And this is actually not surprising because you have probably had this in your kitchen, aluminum foil. You know that aluminum is very, very reactive in our kitchen. How is that possible? Well, the reason it's possible is because it reacts with air and forms an oxide, and that protects the metal from additional reactions. And the liquid metal does exactly the same thing. So here's this oxide layer. You can see this is from an electron microscope. This layer is a few nanometers thick. You don't really think about it when you look at the metal. It's almost inconsequential, but it's very important for protecting the metal. And for us, it's very important because it affects the way this stuff flows. So this is probably the most important slide, so please watch. This is the metal spread out on the glass side, and we use a little bit of acid from the Q-tip to dissolve away that oxide layer. So without that oxide layer, the metal has very large surface tension and just feeds up. But with the oxide layer, we can kind of spread it around like wet paint. And so this allows us to do things like pattern this material into things like wires. So we published this review, and there's a lot of information here. I'm not going to go through every point here, but just to kind of point out a couple things that are interesting. One of the things the oxide does is it kind of forms a wrapper that goes around like a skin that goes around this metal. And so this allows you to 3D print the metal. So here we're dispensing the metal from a syringe, and that oxide layer forms so quickly that that you could basically see it immediately if you suck the liquid back into the syringe. Dispense it as little droplets and start stacking them. It will form 3D shapes that hold their shape. Again, this is all because of this 3 nanometer oxide skin that forms spontaneously. If you did this with water or coffee or tea or any other liquid that has low viscosity, you would end up with a big puddle. But because of the solid skin that forms on the surface, you can form these 3D shapes. So here we're stacking droplets. You can also do a burst of pressure, and it will oxidize so fast that it forms a fiber in midair. And that fiber is like a garden hose. It's still liquid on the inside, so you can drag it around and make electrical connections. And just as close as we get to biology in my lab, it's a dead bug. These are the eyes of the bug, if you can't tell. And so we are, in this case, just for fun, printing antennas on top of an insect, which my student did as a joke. But I really like this because it shows how gentle this process is and how small these structures are. So they're on the order of a few hundred microns. Okay, so we can 3D print the metal. Now, another thing, way to pattern the metal is to actually modify the way it flows. So we call this rheology. And the truth of the matter is, and you can maybe gather this from the previous video, if you just try to extrude the metal, you'll get a droplet, just like you would with water. And what we would really like for a lot of printing applications is to have something that looks more like toothpaste. So we do this in a way that's very, very easy. We just take the metal and we stir it. And we stir it for a while, about 30 minutes or so. And doing that, we're constantly exposing the metal to more oxygen. And at the end of the day, you get something that looks like fix. And well, why is that? Because we've mixed a lot of oxide, very thin oxide, solid material into the metal. And so we haven't published this part yet, but if you'll see on the left here is a syringe nozzle where we dispense the liquid metal. It forms droplets, just as I told you. But this paste comes out kind of like toothpaste as a cylinder. Now we've done what's called micro CT. This is a way of seeing what's inside the material, and you see these little dark spots. These are little bubbles of air that have gotten trapped inside the metal because of all these oxide flakes that are inside of it. Okay, so we can pattern it. So this is nice, and we have this idea of taking that foam, which does little pockets, and adding water. And I promise, I know you have a different background than here. I'm not going to show you too much chemistry, so don't be scared. But there is some interesting chemistry. When gallium comes into contact with water, it will oxidize, of course, and produce hydrogen, which is a gas. So we thought, well, what if we mix a little bit of water into this porous material? What will happen? Well, it's a little bit like when you bake bread. You make the dough, and then you wait some time, and it rises. In the case of bread, that's because of CO2 bubbles standing. Here, it's because of hydrogen. So we titled our paper to be a little bit fun and provocative. Liquid metal foams that grow in water. Okay, well, the analogy only goes so far because, of course, plants are much more sophisticated. But there is this idea, and the inspiration for this idea actually came from Professor Kuo from Georgia Tech, who's doing this really beautiful work on hydrogel materials that grow, not just swell, but actually grow. In other words, they're adding mass. So we did this, and this is a sped up video of these gel materials. And we actually don't want this to happen too fast because we want to be able to print them and then have them grow later. But the exciting thing is that if you look with the CT and look inside the material, you don't just end up with one giant bubble of hydrogen. You end up with this really nice uniform morphology that grows uniformly, and it's actually conductive. Okay, so what is this good for? Well, in some ways, this is a little silly because everybody who does 3D printing is trying to make things smaller and higher resolution. But here we print and it actually gets bigger. So I mean, maybe it is. I don't know. But one thing we did do was we made a circuit with some LEDs, and we took this foam material and we had it over time grow through kind of this labyrinth and connect the circuit. So to me, the thing that's cool about this is the foam that can grow, and it's got pretty good conductivity. All right, coming back to this slide again, it's just sort of an outline. Another way to pattern the metal that's very unique, you cannot do with copper, you cannot do with aluminum, is to other container, inject it like a liquid. So here we take microfluidic channels, these are small tubes, and we apply a little bit of pressure to the liquid metal using a syringe and inject it into these microchannels. And so here's one, and then we're going to do another one. Here's an inlet, here's the outlet, and it just flows right through. It's enough to break that very thin 3 nanometer oxide there. Think of it like glass, the 3 nanometers thick. It's not very hard to break. And because of the low viscosity, it flows right in. Now, once it's in there, you've made wires that take on the mechanical properties of polymer. So check this in rubber. You have a rubber wire. So we've used this to make different antennas. This is called a dipole antenna. Coil for transmitting power, and then electrodes for microfluidic. All right, so here's just kind of a cool demo. I'm not sure if the sound will work here, but this is liquid metal that we've injected into a rubber tube. Not going to be simpler. You buy a rubber tube, inject metal, that's it. So, look at the sound like. So, we cut off the headphone here, so we cut it sitting over here, so no sound is coming. All coming from right here. It's like this. The degradation sound quality. It actually give a metal, so the stretchability is up. This. So one of I had a really good undergrad, super talented professor, that took these wires and he actually took 3 of them and kind of twisted them together. So this looks like one wire, but there's actually 3. He uses this to measure capacitance between his finger and these fibers. So it's very much like how your cell phone screen works, active touch sensing. And we're able to detect position because each of those 3 fibers are filled with different lengths. So this is kind of cool because it's a touch sensor that's in fiber format that's stretchy like rubber bands. And then, I tried to pick out little examples that I think have robotics applications. There was this really nice work from several of the people that I've listed down here at the bottom, Kurt Shea and Gary Oriana, where they did what's called electro-adhesion. This is a way to make a gripper. And let me explain to you how this works. If you have electrodes that alternate between, say, positive, negative, and you put them inside of an insulating material, then there are electric fields that emerge from those electrodes. So those electric fields are depicted by these blue lines. So there's an electric field here, but also a diverging electric field that goes down this. So if you bring an object, and the object in this case, you can imagine it be a piece of paper or an apple or something like that. It's this gray box. So in this little video, our object is this piece of aluminum foil, and we draped a weight from it so that there would be some gravitational force pulling this down. And our electro-adhesive device is sitting right here. You can't quite see it because it's blocked by the foil, but this is what it looks like. It's inverted shape like we put them out. We apply a voltage to it by these two electrodes, which you can see here. Positive, here's negative. Now, it's currently using electro-adhesion, but when you turn the voltage off, no adhesion anymore, the thing just falls. Okay, so you don't have to use liquid metal to do this. Factory work that people did. Not use liquid metal. But there is at least one advantage of doing this. One is it's stretchy. But the other thing is when you stretch it, you strain the material, you change the geometry, right? And that changes the amount of force of the object that can be held. So as you strain the material, the amount of force will go up. Because the electrodes get closer together, and therefore you let go. This is interesting for robotics that can be controlled electrically. Another thing that you can do with liquid metal that I think is interesting for robotics is to change kind of a silly picture of a variable stiffness on your muscle, right? So you can imagine the way that we do this. We take the liquid gallium, we inject it into a soft elastomer that's stretchy. You can form it in any shape you want. In this case, it's fine. Stretch, and then you solidify it. That is pretty simple. This video shows one of these wires that's frozen, and because we use gallium, it is solid at room temperature. So we froze it into this shape, and it will stay in that shape forever and ever. And then we dip it into some warm water. We could have also used our body temperature to melt it. And when it melts, it becomes very, very soft. You go from being solid, malleable, being soft, like a rubber. Now, there's some drawbacks to this approach. Nevertheless, it's potentially. Okay, so previously I showed you this idea of injecting the liquid metal. So we had a microchannel where we had an inlet, and we inject the metal this way. And as we're injecting it, air comes out the side, out the outlet. In this example, there's no outlet. Inlet, but it's a little hole, and over it we put the liquid metal, kind of like an ice cream cup. Whole liquid thing. Then put the whole thing into this vacuum chamber, and we pull vacuum for 20 or 30 minutes. What that does is it pulls the air out of this silicone material. So you can maybe faintly see there's some channels in here that we've patterned lithographically. And so when the student, Yulian, comes out and over and turns this valve and lets the air back in, let me show you what happens. First, you're going to see the thing flutter. So here's its reflection. You can see because it's shiny. There's the liquid metal. The air is going to come into the chamber, causes it to flutter. So now atmospheric pressure is pushing here, but these are still under vacuum. Very simple, kind of hands-free way. Tighter. I was still out of my chair myself. That was very cool. All right, so what does this allow us to do? Well, one of the things that we did recently that I think is quite interesting, that generally speaking, materials that are stretchy, like soft robotic materials, tend to be highly gas permeable. So high stretchability, like a piece of rubber, tends to have high permeability. So if you want to make something that has low gas permeability, use something like a metal. And if you don't believe me, maybe at lunch today, look inside your potato chip bag or maybe you go from your memory banks. Think about the shiny. It's always shiny on the inside of one of these metals. Why? Plastic is not a good enough barrier. You have to have enough layer of aluminum to keep your potato chips fresh. So we wanted to make something that goes up into the top quadrant here. In other words, stretchy but gas impermeable. And you might imagine how we did it. We combined rubber with lithium metal. And why would you want to do this? Well, one thing that's my application is to make stretching devices that have good gas barrier properties, like a stretchable battery. Batteries are always contained inside of rigid housings for a number of reasons, but one of which is you don't want the liquid inside to evaporate. Our battery dies because the water below every time that happens. And you also don't want the oxygen to get in. You know, right? That's bad news for the battery. So we made a stretchable battery. Sorry, I should have mentioned this was a collaboration with Cal Ding. So we made our battery. Here it is. Here are the electrodes of the battery sticking out the back. Here's the packaging that's going to keep all that liquid inside. And if we measure the mass versus time for this good barrier material, nothing changes, which is great. But without it, remember that silicone is very permeable to oxygen and to liquids, and so mass actually drops. So people have published stretchable batteries, but unfortunately, the reality is over time they just fail because the stuff just goes through the stretch meter. All right, so another kind of dirty secret, a lot of stuff that I've shown you use silicones. They kind of have the best mechanical properties, which is why we're working on trying to make materials tougher. They tend to tear very easily. They're very easy to work with. Right. So I'm going to tell you it's a bit of a story, but see here going into a sabbatical at Microsoft. Guy that works here named Bill Gates. Doesn't even come by the lab that was visiting. Yes, man, I really want to show him the sick virus, but Bill Gates is a very powerful person. I didn't want him to do this. It should be great. So I started thinking about this, and one of the ways that we address this was in Steve Craig's lab at Duke, collaborated. And the idea was to include this molecule. I think this is the last molecule. You'll notice in this molecule has these ring-shaped structures. Just like if you go to the hardware store and buy a chain, you can say it has rings. Pull that part up, eventually molecules do the same thing, and it turns out in this one, when these chains, when these rings break, they change color. So this is our clear silicone material, very common silicone. It's got this molecule in it. You can't see it because it's transparent. And there's this little line, which is our liquid metal wire. And now we start pulling on it. And at this point, I'm starting to get a little nervous. I'm like, Mr. Gates, please, stop. You're about to break it. But before it breaks, those rings open, it changes color, warn you that you reached the breakage point. Then when you let it go, purple. When you let it go back, those rings will flip. After being cynical, which you should be a little skeptical here, I'm a little worried if you did this, you might say, oh, I'm going to stretch it. See. Flexible limit. So this is not a perfect solution, but this was a product of that experience at Microsoft. And so that also led me to be thinking about color changing. Right now, we're looking at a screen where the colors are constantly changing. How do we do this in a way that's soft? Well, it's actually quite easy. You can just take this same concept that I showed you, inject liquid metal with silicone, and in this case, we're adding this blue pigment. And the blue pigment, when it gets warm enough, turns white. So we just run electricity through this, and we get. And there's different pigments. So this is a red pigment. And running through it, and it changes white. So it's kind of cool. It's soft. It's strategic. But honestly, there's nothing new here. There's no new chemistry. In fact, you can see that from the thermal image. That's just thermal effect. So why is this interesting? Why is it worthy of a publication? Well, one more thing. Okay, so if you combine red and blue together, here are two pigments mixed together. It looks purple. And if you ran a little bit of electricity, that red pigment will disappear at a lower temperature. So now it's blue. And then as you run more current through it, you get blue. Get multiple states, but new physics and then new chemistry. So why is this interesting? Well, what's interesting is because metal in a soft material allows us to start doing some kind of chemical deformation. So here you can't see it, but there's liquid metal circuit inside of here. The purple stuff is from this pigment, electrodes on both sides. And we're not running electricity to get warm enough to change color. However, when we squeeze it, we put it like squeeze it, we change the local resistance. And when we change the local resistance, we get joule heating. So this is kind of interesting because it's now responsive to touch. When you touch it, it starts changing its color. And well, if you want to think of it, kind of say it in a more fancy way, what we're doing is we're coupling mechanical and electrical properties and optical properties. So what do I mean? Take the liquid metal wire, you stretch it, you make it more resistant. That's it. So here's a demonstration of that. Again, the purple color comes from the pigments. We're running current through it, but not enough to cause color change. And then we start stretching it. And when we stretch it, we change the geometry. We make it longer, and therefore more resistive. And so it starts to change color. And this is kind of neat because I showed you the thing about Bill Gates and you wanted to keep color morning. Well, with the chemical approach, you can't control the strain at which the color changes. But here, based on the amount of current and the geometry of the liquid metal, you can actually control when these colors will change. All right. So why is this interesting for robotics? Well, color change kind of looks cool, but to me, this is where it gets really interesting. Think about maybe doing this at lunch today. Say there's an apple sitting with your arms. Come in and go grab it. Typically, what we do is we use our eyes to see the apple, and then we wouldn't even have to use our eye to figure out proximity. That information goes to our brain, and through what I consider to be magic, we respond. Apple with the gauntlet. Happens so easily, but it's so complex to replicate. Okay. Now, if you were wanting to replicate this, you might make in a robot, you might make a sensor, a computer to process information, a motor. But what if we could do this without a centralized processor? And this is not a perfect analogy, but there's a thing called a duplex complex or two like in that case, the signal is not going all the way through brains. Happens to that, you can really consciously control what you're playing. So we thought, well, okay, could we do this? And it turns out that vertebrates like us tend to have almost all of our neurons centralized in our brain, in the skull of our brain. Whereas an octopus actually has the neurons distributed in their arms, where the two nerves are. From a robotics, this would be very interesting to you because how do you control this? If this arm has a brain, this arm has a brain, it goes see through it. There has to be some centralized coordination. I think there is, but I don't really think. All right, so basically we want to make something like an octopus. That would be it's really cool. How far we are from doing this. But anyway, here's the idea. We take this soft, squishy material and we make this little circuit labeled A, B, and C. And basically the current goes from this point to this point through those three sources. So that's just parallel circuit. Flip it over so you can't see the liquid metal. The liquid metal's underneath. So you see the purple color from the pigment. And we're running current, but again, not enough to cause. Then push in region A, we squish this region. To do that, we divert more current to region C. That happens, we get color change. Then if we push A and B, start to see that there's like a little bit of a logic. And okay, this is great. But There's no transistors here. There's no neurons here. And the entire thing is solid. We just said, okay, what if we said, okay, color change is nice and get nice and swish, but better way to do this. So we thought, okay, here's this a little again silly, but Venus flytrap. Venus flytrap have these little hairs are a bit difficult to see. There's no there. And the idea is that if Venus flytrap section grows through lands there, it's not clear to it doesn't know it's that close. Right. So that when an insect lands in there, it's going to move around and it's going to touch this and this and this and that touch a couple places. So we used the same principle, but instead of a slab of material, we made liquid metal wires that are like here. Instead of color change, we hook these up to a circuit so that it can power a motor or power an LED. So if we switch A, it's a bit hard to see, but the LED is on and the motor's on. If we switch A and B, then the motor turns off and the LED stays on. So again, it's a bit of a truth table. And this entire thing is being controlled based on the way it's flashed. So if I were to dumb this down to my level, I would say this is just a variable resistor. But what's cool is if you start thinking about it as a circuit element, you can combine these other things in a clever fun. Product arm, maybe. So I mentioned this I'm jumping all over the place, but I really want to make sure I talk about things you guys are interested in. So I want to spend a little bit of time talking about actuators. Very interesting for robotics and for soft actuators, is how motivated this will talk. And this is a very unusual approach to doing actuation. The metals have enormous surface. Butter. Okay, yeah. Okay. Don't worry. 72. What does that mean? Well, it's a high, water has a high surface, 72. This, 700. Okay, so what does that mean? That means like, you can walk around campus and you see most people are like 5 feet, 6 feet tall, something like that. Suddenly you see somebody who's 60 feet tall. This is an anomaly. This is very unusual. You do not have a liquid like this in your day-to-day life. So very large surface tension. And here we've got it in sodium hydroxide, so there's no oxide. Well, can we use this? Actuation. So there's two different ways to do this. I'm going to walk you through it. The first one is called continuous electro-wetting. It's a bit of a mouthful, but the idea is you put this drop of the liquid metal in, say, like a tube, and you apply a voltage across the ends of the tube. There'll be two here and here, and ions that are at the surface of the metal, this is called an electrical double layer, will get shifted to one side and lower that surface tension, and therefore the force on this side is bigger than this side. So it's All right, if you didn't follow me, let me show you an example. So here's some liquid metal inside of a glass tube with some water. You can see the water sticking on the outside, and we've got electrodes on this side and this side. And we're only applying about 1 volt. And when we do this, we can get the metal to move. So we apply voltage, and then we switch the voltage, positive 1 volt, negative 1 volt, back and forth. You can get the metal to move. And it can actually move quite quickly. So here we sweep the frequency, and we get a little plug of metal to move. Now it moves faster and faster until it can't keep up anymore. But you can see as a higher frequency, you get lower amplitude. It just doesn't have enough time shifting back and forth. All right. So this is not really an actuator yet. Well, we're actuating metal, but it's not a useful way. So this guy, Xiang Tang, one of the best researchers that I know, came up with this idea of putting the liquid metal, instead of it in a tube where it can move back and forth like this, put it in a container, which is this green thing, this little plastic container. And these are the electrodes on both sides of it. And now, when that metal wants to move, it's going to hit that container, pump it, right? It's like we pump it into the shape. That's it called this. Here's a video, and he made this little racetrack for these things to move around, so it creates torque. So here's a little motor that he made using that concept. And well, I mean, it's not the best motor in the world, but it's kind of cool because again, it's driven by a surface tension. 1 volt called surface tension gradients. That's the use of continuous electrowetting. Another way you can do this is by something that's going to be a little bit uh, perhaps confusing because it's very unusual. But if you take a droplet of liquid metal and stick the electrode directly into it, then you can get it to react and form chemical. What does that mean? All right, so let me show you an example. This is a droplet of that liquid metal in sodium hydroxide, which again is a base that dissolves away the size there. And you can see the wire that we're sticking into this metal. Now, you told me this 10 years ago that you're going to apply a voltage, positive voltage, oxidation of the metal. I would have expected this an oxide shell to form on the surface. Let me show you what happens. So this is like a little mold that you're looking top down. Here's the mold. Here's the counter electrode. And it spreads like crazy. Really surprising. So over here on this counter electrode, you see the bubbles forming. That's because the water is getting converted into hydrogen. So we're reducing the water and we're oxidizing. It's a long story, and I'm just going to tell you the short version of it. The short version of it is that oxidation, electric oxidation lowers the surface. Last question of the day. Lower the surface tension of water. How do you do that? A plus, good job. You go. So if you take oil, say oil like this on your skin or hair, and you wanted to get it to go into the water, say from your shower, you add a surfactant. Now, as you know, it's very easy to put soap into water to get it to go this way, but it's not so easy to remove. And in our case, we apply 1 volt, and we deposit our soap, for lack of a better word, which is the oxide, and negative 1 volt, we make it go away, and put it back to being that really tall, giant, really large surface. Okay, so what is this good for? Well, before I show you, I'm going to show you some kind of robotic applications. But I asked you all, what is the surface tension of water? And I kind of drive this home with this bar chart. And nobody really has a good sense for surface tension because it's really a force that's only relevant in simple landscape. Do something that's horribly unscientific. But I'm going to keep the numbers the same and cross this out and write mass. Because mass, we all can relate to that, right? Gravitational forces. Okay, so water is at, remember 72? Water is a 72 pound dog, if you want to think of gravitational terms. And if you add soda, it's a 30 pound dog. It's a solid dog. And liquid metal is a 600 pound polar bear. So that's a 60-foot giant that you see walking around on campus. And we apply 1 volt, it goes down to 9. It's completely reversible. You can go back and forth, whereas the dog, once it shrinks, it's like a smaller scale. Okay, so how do we use this? Well, here are these droplets of liquid metal. And remember, they're squeezing. They're like squeezing. For holding that weight up. But when you apply that volt to this and lower the tension, it gets pushed, but it's completely reversible. So you can go back. So they say, okay, that's great. It's an actuator, reducing surface tension. This idea of applying voltage to get a change in tension to get a force. Well, what about robotics? Well, Xiang, this guy I mentioned before, put this concept into a tail of a fish. And again, it's not very fast or impressive, but it's getting surface tension. Well, I skipped over kind of the fundamentals of how this works. And I don't really want to spend much time on this slide other than to say what we're plotting here is the surface tension versus voltage. And these are data points from experiments that we did. And you can see the surface tension is getting lower and lower and lower. And oh my gosh, it looks like it's going to go to 0. How did I let my student graduate without taking one more data point? All he had to do was print the bigger voltage. I'm a horrible advisor. Well, let me show you what happens when you apply this voltage, there's a liquid droplet, and the electrode is beneath it. So you're looking top down. Gravity is pushing it into the screen, and this is where we apply that voltage, where it looks like it should go to zero. This is the 600-pound polar bear that really wants to be a sphere. We're getting it. Suggests the surface tension is very, very low. The electrode is here. When these things break away from that electrode, the metal just speeds up because it's. So the point here is that electrochemical reactions are causing the tension here. That looks cool. I don't know yet what that's good for, but let me show you something in terms of actuation that's really, really cool. All experience this. If you've seen a dripping faucet, right? Faucet, the water will break up into droplets. You say, okay, great. I don't get the cylinder. I'm just going to turn on the faucet a little bit faster. And sure enough, you can do that. And this is what's called, people call in the literature, a jet. So liquids will come out, but they'll still break up into droplets. You see this part of it. You can spray a cylinder of liquid, but it breaks up into droplets. It's called a Rayleigh instability. This has been known since the late 1800s. Hundreds of papers have published on this, and they all say the same thing. The surface tension causes breakage droplets. Right, so here is our nozzle, and we're going to pump the liquid metal. This is about the size of a human hair. Pump it, and of course, it forms droplets because this is an enormous surface tension. But as we start applying voltage, tension lower and lower, and we start getting to that data point. Sorry, I told you why did I let that? Well, that data point where we saw the fractals, it comes out as a wire, no surface tension. Now, if we apply too big of a voltage, we deposit too much. Let's see. Back ahead. I haven't studied that because it's very complicated. Anyway, so we said, okay, let's make one of these cylinders. What if we just get a bit of time? What if we let it fall along? Maybe it'll break up into a droplet. You're going to have to squint your eyes because it's very small, but here's our nozzle, size of a human hair, 100 microns, and here is our wire. I'm going to play the video. So where I'm pointing, that's the wire. Barely see it. It goes all the way down. Very low. Right, so do you guys remember mid-back actuators? Do you remember this from question? How do you? This well, yeah. So I think that's how you define current. But yeah, so current. So either way, you have current going through, say, a wire, and you put a magnet behind it at 90 degrees, you're going to get current source. Normally, we don't observe this. Think about it. All and usually wires are rigid. We have a liquid metal wire. Well, it's a liquid, so it should respond to the force. And in this case, we're oxidizing the surface, which means we're stripping electrons from the metal, which means we have current liquid wire. Well, okay, there's one other thing I need to remind you, which is Lenz's law. And is that you have a magnet. So say this is north and this is south. The magnetic field lines go up like this. Get close to the surface, those magnetic field lines are parallel. What Lenz's law says, if I move a conductor through that and I get to the edge, it starts to diverge, the conductor will slow down. So you're going to see both of those things beautifully demonstrated here. This is a collaboration of these folks here from Australia. And again, here's our nozzle. If you didn't know any better, you would expect droplets to form, but I've already showed you can form wires. We put a magnet behind here. I'm going to make the magnet disappear. So gravity makes this thing fall, forms a wire. We can get it to whip around, and it slows down at the edge of the magnet. You guys are pretty impressed. Okay. If you're not impressed, go home tonight. Faucet, standing water. Remember, it's only 72, not 7.8. Come out with a cylinder. Size of human hair. You will not be able to, but if you can, then try to get it to spin around in mid-air and form the shape. Okay. Another sort of robotics thing. This is a really cool actuator in Dreyfus. Imagine if you just have a soft, like, cylinder that speed, all it's gonna do is just sit there and squirm around. What you need are feet that can, stick to a surface and let go, stick, let go, stick, let go. So we've done this with liquid metal. And so this is a droplet of the liquid metal. And where you can see there's a wire connected to it. And we're applying the voltage to deposit that little thin oxide there on the surface. When that oxide is there, it likes to stick to glass and others. So when the voltage is, in this case, turned off, metal droplet just rolls down and keep it. Touch is very slippery. So the idea was to take these liquid metal droplets and put it into the feet of this little robot. So there's one here, 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 here. And then in the middle is this shape memory alloy that expands and contracts. So what we do, as you might imagine, is make these two legs sticky, these ones slippery, and then switch it back to the feet. So here it is looking top down, and there we go. Okay, so now you can see the body expanding, contracting. This is all underwater. The adhesion of these feet, and all driven by small voltages and using interfacial chemistry of. All right. Well, I had one more thing I wanted to show you. Maybe I can show you very briefly, but coming back to kind of come full circle here, talking about these actuators, lock robots. There's one little thing that's always bothered me about this, and maybe bothers you too. Look at these little cables. Where are they going? Well, they're going to some pump that's applying pressure and relieving pressure. We have this really beautiful soft thing that looks like an octopus, but then we'll call this tethered. It's tethered. There's two things. So we thought, well, what if we could use electrochemical reactions to generate that gas? And well, you might argue we still have tethers because there's wires, but we can make these wires go away by using batteries. All wires are all on board. So we're going to apply a potential here, and we're going to convert this hydrogen, which has water in it, to hydrogen gas. So this is going to reduce, this is going to oxidize. So on the left, we're going to generate hydrogen gas, and it causes this thing to inflate. And on the right, there's some oxidation reactions. Now, this has some advantages. There's no pumps. It's controlled electrically. It uses the water from the body of the robot. That's kind of cool. And it creates reactive species, which could do stuff, but it's very slow. So skip this, but we've used this to make little grippers. So again, very slow. You see this is sped up 8 times. So it doesn't work great in terms of speed, but it is kind of interesting because it's set out at 8 voltage pump. We're doing this electrically. All right, so just to conclude, do you guys know this guy? Fires, starting out loud.
Scientists at North Carolina State University announced they discovered way to move and manipulate liquid metal with electricity. And Arnold Schwarzenegger has already been sent back in time to stop it.
That's an into my good This was also my career highlight. So there's a lot of words here, but I definitely have to show you that these are really interesting. We're dabbling in ways that they might be used in robots. Some of them probably not as practical, but I think some are compelling and very unique. This work was done entirely by students that I did doing. Picture of my group from last spring. We went to get hit. I'll take you for some howling cow ice cream. And sponsor this over the years and just some resources that you want to read.